All right, Algebra 2. We are in Chapter 2, Section 7, which is Applying the Fundamental Theorem of Algebra. It's a really fancy title. It always used to scare me, but it's not scary. We'll explain it. It'll be okay. Let's start out with some warm-ups, though. What is the degree of the following polynomial? So I have f of x equals 8x to the 6, yada, yada, yada. The degree is always the highest value exponent. So here I have the degree is 6. And then when I need to solve something, I factor it. So whenever they say solve or find the zeros, etc., I factor it. So I actually can't factor anything that multiplies to a positive 3 and adds to a negative 2. So I need to use the Pythagorean theorem. So negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So simplifies to 2 plus or minus the square root. I get a 4 minus 12, which is negative 8, all over 2. Negative 8 breaks into 4 times 2, 2 times 2, so I can factor out a 2 from the radical, 2 plus or minus 2 root 2, but I can't forget that negative, so there's an I there. There's a 2 in every single spot, so those can all cancel out. And my final answer is 1 plus or minus I root 2. So 2 solutions, because I have a degree of 2. They're both not real, though. Okay? All right, into the lesson. The equations x cubed minus 5x squared minus 8x plus 48 equals 0, which becomes that nicely factored problem. We've got lots of binomials there. It becomes that when factored. It has only 2 distinct solutions. This binomial here gives us a solution of x equals negative 3, and this binomial here gives us a distinct solution of x equals 4. But because this binomial appears twice, you can count the solution for twice. So with 4 counted as a repeated solution, this third degree polynomial, there's my third degree polynomial, has 3 solutions. Negative 3, 4, and 4 again. The previous result is generalized by the fundamental theorem of algebra, first proved by a German mathematician, Carl Friedrich Gauss, he lived a long time ago. So basically, the fundamental theorem of algebra, if f of x is a polynomial of degree n, where n is greater than 0, then the equation, when it's set equal to 0, has at least one solution in the set of complex numbers. So I've got a polynomial of degree n. The equation has to have at least one solution in the set of complex numbers. Corollary to that, which is just like a secondary rule or a secondary law, if f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has exactly n solutions, provided each solution repeated twice is counted as 2 solutions, just like up here. Each solution repeated 3 times is counted as 3 solutions, and so on. The corollary to the fundamental theorem of algebra also implies that an nth degree polynomial has exactly n zeros. So a third degree polynomial has exactly 3 zeros. So how many solutions does this equation have? Well, I'm a degree 3, so I'm going to have 3 solutions. How many zeros does the function given have? Well, if I'm fourth degree, then there's going to be 4 zeros. How many solutions does this equation have? Come on, guys. That's a funny 4, isn't it? 4 solutions. Sorry, I'm not going to let that stay there forever. There we go. Dot my I. And how many zeros does this function have? I'm a third degree. 3 zeros. All right. So now to talk about the behavior near the zeros. The graph of f in example 2 is shown at the right. Note that only the real zeros appear as x-intercepts. Also note that the graph is tangent to the x-axis at the repeated zeros x equals -1, but crosses the x-axis at the 0 x equals 2. This concept can be generalized as follows. When a factor x minus k of a function f is raised to an odd power, the graph crosses the x-axis at x equals k. So x minus k, the factor is raised to an odd power. 1 is odd. The graph crosses the x-axis at x equals k. It's a 0 right there. Or it's a solution right there. Cool? When the factor x minus k of a function is raised to an even power, that's an n, raised to an even power, the graph of f is tangent to the x-axis at x equals k. So here it crosses because it's an odd power. And then here, because it's an even power, it's tangent to the x-axis, right? So we have tangent to the x-axis at x equals k. It's still a 0 there, or a solution. Yikes. Find all the zeros of the polynomial function. So the possible zeros I have are 1, 2, 7, and 14. Let's do this. I don't know why I'm in red, sorry. Coefficients. Sorry. So 1, -4, +4, 10, -13, and -14. Multiply, add, multiply, add, multiply, add, multiply, add, and multiply, add. So I just got it down to a 4th power, which is grand. Not really helping me much though. So I'm going to go ahead and go again. I don't have to rewrite my coefficients when I do this. I can just go. So multiply, add, multiply, add, multiply, add, and multiply, add. So now I'm to the 3rd power. Still doesn't help me much. So right now I have x plus 1, x minus 2, and x 5th, 4th, 3rd power minus 3x squared plus 3x plus 7. Still can't do much with that. So I went ahead and graphed this on Desmos. And what I see on Desmos is right here. First of all, I have an odd power. I know my odd powers are going to look like this. So I come up to -1, down, and back up to 1. So this right here is -1. Sorry, and this right here is 2. So what that tells us is when it's just a touch, right? That's a tangent 1, so that is an even power. So this tangent 1 right here is going to happen more than once, this tangent 1. So I'm going to go ahead and run the -1 again with my synthetic division. So I'm going to multiply and add, multiply and add, and multiply and add. Cool. So I'm going to move to a new slide and continue on. So at this point, what we see here, I drew this graph on Desmos, and I found a solution here, which is a tangent. Remember, that means it's an even power, so it'll happen more than once. That's going to get me x. Make sure I get it right. Yep, x plus 1 twice, and x minus 2, and then we had x squared minus 4x plus 7. So I've factored it completely, but I don't know all of my solutions. This solution right here gives me x equals -1 twice. This solution gives me x equals 2. I need to solve for this one. I need the quadratic formula for it. So -b plus or minus b squared minus 4 times a times c all over 2a. So 4 plus or minus the square root of -12 all over 2. I don't know why that square root is so large. 12 breaks into 2 times 6, 2 times 3, so the 2's come out. 4 plus or minus 2i root 3 all over 2. I can simplify. That leaves me with 2 plus or minus I root 3. So I got 1, 2, 3, 4, 5 solutions. Cool. All right, find all zeros of the polynomial function. So plus or minus 1, plus or minus 3, and plus or minus 9 are my possible zeros, right? Cool. Let's just try 1. Coefficients. I don't think 1's going to do it. I multiply and add, multiply and add. Nope. That's not going to cut it. Let's try -1. Multiply, add, multiply, add, and multiply and add. Cool. So I'm down to squared. So far I have x plus 1 times x squared plus 6x plus 9 equals 0. X plus 3 times x plus 3. Yeah. So that gives me x equals -1, -3, and -3. If I graph that on Desmos really quick, I get a touch at -3 and a cross at -1. if you remember, the touch means that it happens twice, or an even power, but I only have 3 degrees to go from. So the touch means this one happens an even power, or in our case twice, and then it crosses, it happens an odd power, or in our case just once. Okay, last one, find all the zeros of the polynomial function. I'm at a 6, so plus or minus 1, plus or minus 2, 3, and 6. All right, let's try it. I'm just going to willy-nilly pick one to try. Coefficients are 5th power, 4th power, 3rd power is missing, 2nd power, 1st power, constant. Multiply, add, multiply, add, multiply, add, multiply, add. Cool. That's the 1st power. I need 5, so let's try 2. No idea. Oh, multiply, add. It's a positive 1. Multiply, add. 2 times 1 is 2. Nope, that doesn't work. Okay, let's try negative 2. So, multiply, add. Negative 2 is positive 6. Add. Negative 10, negative 3, positive 6, and 0. Cool. So I've got 5th power down to 4th power, 3rd power. I know I'm probably going to have one of these duplicates. I don't know if it's the 1 or the negative 2. So let's just go ahead and try the 1 again. 1, negative 2, negative 2, positive 3, 0. Cool. So it looks like I have x minus 1 squared, x plus 2, and x squared minus 2x plus 3. Okay, I can't do much with that one. So I'm going to go ahead and use the quadratic formula on the next page. X squared minus 2x plus 3. So negative b plus or minus the square root b squared minus 4 times a times c all over 2a. So this would be 2 plus or minus 4 minus 12, negative 8 all over 2. So we've already done that negative 8 one. I have 2 plus or minus 2i root 2 over 2. That means I can cancel this. I'm left with a 1. 1 plus or minus I root 2. So my zeros are 1, 1, negative 2, and 1 plus or minus I root 2. So 1, 2, 3, 4, 5. Whew, good job.